Alright, in this video we're gonna explore the verse of statistics, but not from a mathematical standpoint, but from a computational standpoint. So, in the previous video we showed how to think in terms of probability using Monte Carlo simulations, which is something that was not available until the 20th century. But the main question was like, what if the probability is not known? And it turns out it's not so trivial. It took hundreds of years to go from probability to statistics. And in fact, we already cheated, not only in terms of using computers, but also even the notion that repeated trials converge the probability into the true probability was not initially known. Bernoulli was the first one to define this convergence in the 20th century. So we already skipped hundreds of years. And then it took even more centuries to even begin to think in terms of an unknown probability. So today, probability statistics is well defined mathematically, but let's look at the math to see how that's not, even the modern understanding is not so trivial. So a probability model is this triplet where we have a sample space, a sigma algebra of events, and then P is a function where from a sigma algebra we get a number between 0 and 1. So that's a probability measure. We don't need to understand what this means. This is just to show that the mathematics behind statistics is not trivial. But let's look at it anyway. So then the next step is a random variable. So it's a measurable function where sigma is the sample space and script x is an observation space. So from one element to the sample space, we're going to get an element in the observation space. And the tricky part is that the preimage of x given an event of interest is something we can calculate the probability of. That's a convoluted way of saying that it is measurable. Okay, so this is measurable, and then the estimator is a function of the observed data. So given an observation space, we're going to get, as a result, an element in the parameter space, and theta hat is going to be a function that, given some events, measurable events, we're going to get an estimate. So what does this all mean? So theta is what we are looking for, and theta hat is an estimation of what we are looking for. But we don't need to understand any of the math. So let's go to computing. Let's do a Monte Carlo simulation to try to find what does this all mean. So let's say theta is 0.5. That's the probability of getting heads in a coin flip. So this is going to be a binary situation. We're gonna do 100 coin flips, and this is the result. How many times did we get heads? Okay, so we get the mean of x is, so 54 heads divided by 100, we get 0.54. This is theta hat. This is the estimation of theta. As we can see, this is close to this. That's what all the math means. Now let's plot this. So we know the estimation of P is 0.54, and this is a graph showing that as the number of trials increase, the estimation of the probability gets increasingly close to the true probability. It's never going to be exactly the same, but it converges to that. Okay, but so far we haven't done anything new. This is exactly the same as we did in the previous video. So what is different about probability? Sorry, statistics. Well, what is different is that we don't know theta. Here, theta is going to be a random number that we don't know. And that's what we want to find out. That's how the real world operates. In the real world, we don't know the true probability of anything. So, in this estimation is 0.44. If we look at the graph, this is what we see. So, is it 0.5? Is it 0.45? Is it 0.4? We don't know. This is just an estimation. So, is it reasonable to assume that theta is 0.44? In the real world, we cannot know. But here, we can cheat and figure that out. Actually, 0.46. And we can do the same again. Like, let's get another theta. We don't know what it is. Let's do an estimation, 0.47, right? This is our new estimation for an unknown probability. But we can do another estimation. Now it's 0.48. So it's reasonable to assume that it's around maybe 0.485, right? We can do another estimation. Okay, that's pretty far, so maybe 0.52 or something like that. In the real world, we cannot know, but here we can figure out what is the real theta, 0.51. So that's what this is. Theta hat is an estimation given some input data, which is going to be random. We're going to have a parameter space, which is from 0 to 1. So that's our estimation. So we could end the video there because that's basically statistics, is given an unknown probability, what is the actual probability. And the truth is we can never know. But we can skip ahead hundreds of years to the notion of a confidence interval. And this is where statistics really get to be useful to try to define the real world. This is how Fisher thought about statistics. So theta is the unknown probability that we are looking for. Theta hat is an estimation given some input data. So we have this. This is going to be stochastic because the input data is random. This is a function that is going to provide a delta between that estimation given certain data. But again, we don't need to look at the math. We can just look at the simulation to see what these all mean. But then this statement says that what is the probability that data is between this range? And actually we're looking for a probability that is this is basically 0.95. So that's what the probability that we're looking for. So what does that mean? Well, so in this case theta is 0.51. So this is the confidence interval. As the number of trials increase, this estimator um, this estimate it gets closer to the real probability, which we know is 0.51. But what Fisher reasoned is that we are never going to know that, so we might as well provide a big range where we know that the probability of the probability being inside this range is 0.95. It could be here, it could be here, it could be in any number of places outside this range, but that's unlikely. What is most likely is that it's between this range, and in this case we know that yes, it is actually between this range. But let's do the same thing for another theta. Okay, so we get another theta. We do the same, and then the confidence interval for 0.95 confidence level should be between 0.32 and 0.51. Okay, it's a big range, but it's reasonable to assume that is between this. That is statistics in the modern understanding that only came to be like basically 100 years ago. But now we're looking at it through computing, and it's easy to just run these simulations. Now, here we can cheat and find out if data is within this range. And once again, it could be outside this range, but that's unlikely. 0.39, 0.4. So yes, it's between 0.4 is between this range. So that's it. That's taking statistics to the next level, 20th century level. Okay. So now we have understood the basics of statistics from the computational point of view and how it can be useful to understand the real world. But this is just the beginning. Right after defining this, Fisher went into reasoning the concept of likelihood and everything that comes after that. And once again, the math is not trivial, it's useful, but we're going to look at it through the lenses of computation and using simulations. Hopefully you found this useful, and let's explore the more complex topics in the next one.